Okay, so now let's imagine you have a mass on a spring, except for, let's imagine it's in some sort of goo. So there's some sort of viscous drag around it, like maybe you're oscillating it through some syrup or something. Okay, so and we want to find how this thing, what's this guy's time evolution? What is his position as a function of time going to look like? Well, let's draw it out. Okay. So if I have my free body diagram, if he's moving this way, let's say that's his velocity. Okay, let's draw our isolation diagram. Let's see, we're going to have mg, we're going to have normal force, we're going to have the spring is pulling it this way. But if we have viscous force and he's moving to my left, what way is the viscous force? Which way is the drag going to be acting? To the right? So it's viscous drag. Let me just check so I use the same symbols as I use on my slide here. Yeah, we're going to do linear drag here. Let's say it's d times the velocity, x dot. Okay, so if I were to set up where here, this is my positive x direction. Okay, so if I'm going to do my sum of the forces, the x direction, it looks like, well, I'm going to have negative kx. Now I have a force that's proportional. The way I drew it here is actually a little misleading. I apologize. Let's see. What I want to say is that on the sum of the forces here, my viscous force, I should have it going out. All right, we're going to change this. We're not going to have velocity negative x, that's too many double negatives. So let's do velocity this way. And now we're going to have our viscous force pointing away from the direction of motion. That's better. Okay. So now we can say that the viscous force is negative vx dot. You know it always has to be in the opposite direction that the velocity is going, so that's how we get this negative sign. Okay, so we can write the mass times x double dot equals minus kx minus bx dot. So if we bring everything over and divide by m, sorry. Okay. Does this look familiar? Does it almost look like something you did recently in math class? Maybe a little bit? Okay. So if we make some change of variables here and we call that coefficient of x dot 2 beta, where beta is v over 2m. And we're going to keep calling this our omega, except we're going to call it omega naught squared now. Why is it 2 beta? Well, you just did this in math class. I think you said, right? So that factor 2 makes your factoring much easier. You're not going to work through that today. And the answer is that this position as a function of time looks like, let's see, I'm going to be on this screen right here by laser pointer, so to your left. Okay, it looks like this first term, a to the minus beta t. That looks like the amplitude, except for now it has this decaying exponential next to it, if beta is positive. And you still have an oscillation, except for you have now this Planck thing omega 1, which is not on the slide for some reason. So let me go ahead and write it down over here. Okay. So let me write down what the solutions are right here. Okay.
Squared?
Yep, thank you.
No problem.
Is that better? Okay. So what this says is that we have this guy where the amplitude is going to have, the amplitude is going to be scaled by some exponential, and whether it is a decaying exponential or an oscillating exponential, or oscillating, if he is imaginary. Wait, what am I saying? Sorry. Oh, yes, imaginary, absolutely. Okay. Okay, so we have an amplitude that is changing as a function of time. We still have our oscillating cosine function, except for the frequency with which it oscillates is now shifted a little bit. Now it's this natural frequency omega naught, but it's shifted slightly by the same beta that has to do with the damping that it's experiencing. So let me go on to my next slide where I have pretty pictures. Okay. There it is. Okay. So this is what your system looks like in the different realms of damping. So you can see this first one that's oscillating up and down. Oh, my reference is taken on there from hyperfocus. Right? My one that's oscillating up and down, you can see that the amplitude has an envelope around it that looks like a decaying exponential. So amplitude is getting smaller, smaller, smaller as a function of time. This is what we would call underdamped. Critical damping is when this guy is going to decay to zero as quickly as possible. Overdamping, we have just too much viscous force. It's going to get to zero, but it's going to take a little longer. Okay? And I'm going to leave the formal discussion of that for your math lecture tomorrow. So, in summary, what we've learned is that slip around motion is a very general solution to many problems, not limited to simply masses on a spring. And that if you can write your motion equation as something like x equals dot plus some constant times x equals 0, you know the answer. This is x equals a cosine omega t plus phi naught. So slip around motion requires inertia and restoring force proportional to the displacement of equilibrium. The force has to be proportional to x and has to move it back towards what x equals.